Welcome to Factors Affecting Solubility. So, let's examine the difference between vitamin A and vitamin C. So vitamin A is over here, and vitamin C is over here. So in both cases, we've got this ring structure with some tail with a hydroxide on the end. We've got that same sort of structure here, the ring structure with a much shorter tail, the hydroxide on the end. But again, notice in this case, we have, in this ring, attached to the ring, we've got some more OH groups, hydroxyl groups, and we've got this carbon-oxygen double bond here that we didn't have over there. So in this case, this molecule is much less polar. This is a fairly non-polar molecule. It's slightly polar because of this OH group. But this molecule, vitamin C, is much more polar, because we've got many more hydroxide groups in here, OH groups, and we've got this carbon-oxygen double bond. So the vitamin A is largely composed of just carbon and hydrogen and carbon-carbon bonds, whereas vitamin C has lots of these oxygen-hydrogen bonds. And this means that the oxygen-hydrogen bonds are much more polar than the carbon-hydrogen and carbon-carbon bonds, making the vitamin C much more polar than the vitamin A is. And this means that vitamin C has a high solubility in water, whereas vitamin A has a low solubility in water. But on the other hand, the vitamin A has a much higher solubility in fats in our bodies, which means that vitamin A is stored in the body much longer than vitamin C is. Vitamin C is excreted by the body in water, and thus it must be consumed regularly or you get scurvy. So this is why, say, the British sailors were called limeys, because limes contain a lot of vitamin C, and by eating the limes, the sailors were able to prevent themselves from getting scurvy. So, let's look at pressure effects. So pressure has little effect on the solubility of a solid or a liquid, but it can significantly affect the solubility of a gas. For example, high pressures of carbon dioxide are used to carbonate water that we use for soda. This gives us the bubbles in our soda carbonation. So suppose that a solution is saturated with carbon dioxide at low pressure. This means that the rate at which carbon dioxide molecules enter the solution is equal to the rate at which carbon dioxide molecules are leaving the solution. So that's the case like over here on the left. So we have some molecules, some carbon dioxide molecules that are leaving solution. These are the green arrows pointing upwards. We have some carbon dioxide molecules that are entering solution. Those are the red arrows pointing downwards. Note that in this case, there are the same number of arrows of each type. There are 4 pointing down, 4 pointing up. So over time, the carbon dioxide concentration is not changing. So if we increase the pressure of carbon dioxide above the liquid, so we squeeze down on our piston here, this means that the rate at which carbon dioxide molecules are entering the liquid increases. But at first, the rate at which carbon dioxide molecules leave the liquid doesn't change, because the rate of the molecules entering the liquid go up because the collision frequency of carbon dioxide molecules with the surface of that liquid go up as we decrease the volume, because we're packing more carbon dioxide molecules per volume of the gas, so more of them are going to hit the surface of the liquid. But we still have the same number of carbon dioxide molecules in the liquid. We really haven't changed the way that they're moving around in solution. And so we're going to have the same rate at which carbon dioxide molecules are leaving solution, but now we have a higher rate at which they're entering solution. So now over time, more carbon dioxide molecules are going to enter solution. Now after some period of time, our number of carbon dioxide molecules in the solution will increase until the two rates are equal again. So after some period of time, we have enough carbon dioxide molecules in the solution that now the rate at which carbon dioxide molecules are leaving solution is equal to the rate at which carbon dioxide molecules are entering solution. Because we've increased the number of carbon dioxide molecules in solution and decreased the number of carbon dioxide molecules in the gas phase, and thus the rates will be equal. So this effect is described by Henry's law. So this is described mathematically by C is equal to Kp, where C here is the concentration of our dissolved gas, K is a constant characteristic of a particular solution, and P is the partial pressure of the gaseous solute above the solution. So the K there depends on the solute and the solvent. So this means that the amount of gas dissolved in a solution is directly proportional to the pressure of the gas above the solution, because K there doesn't depend on the pressure. So as we say double the pressure, the concentration of our dissolved gas will get higher by a factor of 2. If we double the pressure, concentration doubles. If we triple the pressure, concentration in the liquid triples. So now let's look at temperature effects. So you're likely familiar with the experiment that increasing the temperature causes solutes such as sugar or salt to dissolve more rapidly in water. If you want to dissolve sugar or salt in water, usually you heat it up and they dissolve faster. Now they're dissolving faster for 2 reasons. They're dissolving more rapidly doesn't necessarily mean that the solubility is increased, because as you heat up the solution, the molecules are moving faster. So it may just be that the molecules, because they're moving faster, you're able to achieve equilibrium faster. But in this case, you are in fact moving the molecules faster, so you're achieving equilibrium faster. But you've also shifted the equilibrium point, because most solids have an increased solubility at higher temperatures, but not all of them do. Most of them do, but not all. So, in the case of sugar and water, they do in fact have a higher solubility as you heat up the water, at least to a point. So, but all gases have a decreased solubility at higher temperatures. And this causes problems with thermal pollution. So, if we have something like a power plant that uses water to cool the plant, the temperature of the water increases. So if it pulls in river water from upstream of the plant, it heats up that water a little bit and then it dumps it back into the stream. You're heating up the water in the stream, which means that gases have a decreased solubility at higher temperatures. Fish need oxygen to breathe, and this means that this decreased oxygen can harm fish and other aquatic life if the water is released back into the river or lake at a temperature that's significantly higher than the temperature at which it entered the power plant at. So you can often see downstream of power plants, there's thermal pollution, so there's a significantly lower oxygen concentration in the water than there was upstream of the plant. And this means that some fish, if they're moving through that water that's downstream of the plant, they may not have enough oxygen to survive. So suppose we have a student whose name is Dante. He wants to avoid killing the fish in his fish tank. Dante has a closed or a fixed volume fish tank. He has a cylinder of oxygen gas, a cylinder of helium gas, he's got a heater, and he's got a refrigerator. So what can Dante do to keep his fish tank oxygenated? What can he do to keep his fish from dying? I want you to pause the video and think about it. So, again, Dante wants to avoid killing the fish in his fish tank. He needs to keep the oxygen concentration high. One way he can do that is by increasing the concentration of oxygen above the fish tank, so he can use his cylinder of oxygen gas to increase the concentration of oxygen above the water. Increase the partial pressure of oxygen. That will increase the solubility of water, of oxygen in the water. He can't do the same thing with the cylinder of helium gas. Just increasing the overall pressure is not enough. That will increase the concentration of helium dissolved in the water, but Dante doesn't care about whether or not his fish are speaking with a high voice or not. He cares about whether or not they have oxygen to live. So the cylinder of helium gas is useless to us. What's going to happen if Dante heats up the water? He's going to lower the oxygen concentration. So that's going to be a bad thing to do. Dante, in fact, wants to use the refrigerator to cool down the water in his fish tank. By cooling down the water in the fish tank, he will change the solubility of water, of oxygen in the water. He's going to increase the solubility of oxygen in the water. If you're looking at Henry's law, the C equals Kp. The P there is not changing as it was when we when we introduced more oxygen. But that K value depends on the temperature. Now, that's not inherent, you don't see that in Henry's law, but that K value from Henry's law, that constant, depends on the temperature. And so Dante can either cool down the water in his fish tank, or he can use this cylinder of oxygen gas to increase the partial pressure of oxygen above the tank. He can do that either by pushing out the other gases, or by just increasing the overall pressure, as long as he's increasing the partial pressure of oxygen. If he's got a closed or fixed volume fish tank, he can just pump in more and more oxygen, and so the percentage of oxygen in the air above the fish tank will increase. So that was factors affecting solubility.